Hello and welcome to Vector Flow. Today's topic is neural networks, what they are, how they work, and why they matter so much today. So, what is a neural network actually doing? At its core, it's just a function. You give it an input x and it produces an output y. That's it. The job of the network is to learn that mapping, to find a function that takes your input and produces the right answer. We call the network's prediction y hat, and the entire goal of training is to make y hat as close as possible to the read y. Everything else, the neurons, the weights, the layers, is just machinery that makes that happen. It all starts with the smallest piece, one neuron. A neuron takes in a value, does something simple to it, and passes it forward. But what does it do? It multiplies the input by a number called a weight and adds another number called a bias, which we can represent as this equation. You've seen this equation before. It's the equation of a line, or an affine function, where we have w as the slope that controls how much the input matters, and b as the y-intercept, which just shifts the output up or down regardless of what the input is. Now in practice, a neuron doesn't just receive one input. It receives many, in the thousands or millions. Each input gets its own weight, so you would end up with a weighted sum that we can represent through this equation, or more compactly, as this equation using the sum symbol. That's all a neuron is, a weighted sum of its inputs, plus a bias. Here's a problem though. If every neuron just computes a weighted sum, then stacking 100 of them together will still give you a linear function, since a line on top of a line is still a line. But what if what we actually want to predict looks more like this? You can never get there with just weighted sums, no matter how many layers you stack. The output is always going to be a straight line. You need something that can bend. That's where activation functions come in. The most common one is known as Redu, or rectified linear unit. Any negative input will be mapped to zero, and all positive inputs will just pass through completely unchanged. So, with one bend at zero, that's all you need to introduce nonlinearity to this network. You can then stack many neurons with Redu, and you can, with this current setup, approximate almost any function. Now let's chain it all together. You take a layer of neurons. Each one receives all the inputs, computes its weighted sum plus bias plus its activation, and produces one number. The outputs of that layer become the inputs to the next layer, and that's how a neural network really works. The middle layers are called hidden layers, and data flows from left to right. This is the forward pass. Each layer can be represented by the equation you see on screen right here, and the output layer does not have an activation since it predicts the raw prediction of y. However, if we wrote every single weight individually, it would become unmanageable very fast. Let's take an example. A 512 neuron layer that receives 256 inputs has over 130,000 weights. So, instead of thinking about individual neurons, we think about the entire layers at once. We stack all of the weights into a matrix W, all of the inputs into a vector X, and all of the biases into a vector B. We can see for the equation appear on screen right now. Every row of the matrix W is the weights for one neuron, and the bias vector shifts each output independently. And this entire computation can be collapsed to a single line, which is y hat equals wx plus b, which is just an affine transformation, which is not only cleaner, but makes the computations much more efficient on GPUs. So, now that the network made a prediction, how do we measure how wrong that prediction is? Well, this is the role of a loss function. It measures basically how bad our network did by comparing the real answer to the prediction, or a simple subtraction. This is mean squared error, where it takes the difference between both points and squares it to really punish the big mistakes and punish much less the small mistakes, which makes it very effective on many cases. And so, once we know how wrong our network is, we are only going to try to minimize this loss function, which goes back to just minimizing how wrong the network is, thus making it more accurate. We now know how wrong the network is, but which weights cause the error? That's what backpropagation answers. It takes the loss and sends it backwards through the network, from the output through every hidden layer back to the first layer. At each step, it computes for every single weight exactly how much that weight contributed to the error. This is known as a partial derivative. It tells you the rate at which the loss changes when you nudge that specific weight. Now that we know each weight's contribution to the loss, we update every single one of them with the sole purpose to reduce it. Think of the loss as a landscape. You're on a hill and you want to reach the lowest point. Gradient descent says, look at the slope beneath your feet and take a small step downhill. You take the current weight, subtract a fraction of the gradient, and if that gradient is positive, you decrease the weight. If it's negative, you increase it. Either way, you move towards lower loss. N is the learning rate. It controls how big each step is. Too large, you might overshoot. Too small, and training that network will take forever. Run this forward pass, computing the loss, backpropagation, and updating the weights thousands of times, and each iteration will get you better predictions from the network every time. And this is how neural networks learn. Now let's put it all together. A neuron computes a weighted sum of its inputs plus a bias. An activation function like Redu adds nonlinearity so the network can learn complex patterns. Stack multiple layers, and data flows forward, each layer transforming the signal. We write a full layer as y hat equals w times x plus b. We measure mistake with a loss function. Backpropagation then tells us how each weight contributed to that loss. Mistake with a loss function. Backpropagation then tells us how each weight contributed to that loss, and gradient descent updates every weight to reduce it. That's a full picture. Deeper dives on each topic coming separately. To whoever made it this far into the video, I just want to say thank you so much for watching. This is a very new thing to me, so the editing and explaining what I do. But this channel will be documenting my programming journey as an aspiring software engineer. And like I just said, there will be deeper dives in the next few weeks on backpropagation and gradient descent, which are the most important parts of really how networks learn. So thank you so much for watching. Feel free to leave any suggestions or any questions you have in the comments for me to improve on these. And I'll see you in the next one.